Welcome to qnawire.
All right, this is chapter 22, problem 4 from the Sears and Zemansky's University Physics textbook. It was shown in example 21.10 in section 21.5 that the electric field due to an infinite line of charge is perpendicular to the line and has magnitude E equals lambda over 2 pi epsilon naught times r. Consider an imaginary cylinder with radius r equals 0.250 meters and length L equals 0.400 meters that has an infinite line of positive charge running along its axis. The charge per unit length on the line is lambda equals 3.00 microcoulombs per meter. Part A, what is the electric flux through the cylinder due to this infinite line of charge? Part B, what is the flux through the cylinder if its radius is increased to r equals 0.500 meters? And C, what is the flux through the cylinder if its length is increased to L equals 0.800 meters? All right, so we have 3 parts to this problem, but they're all really just based on the solving for the electric flux in general, and then just the parts A, B, and C are just plugging in the numbers. So the strategy is going to be the same for each of these parts. So first thing as I've done is I've made a basic sketch of the cylinder. The cylinder is given as length L. So that's the length along here. And the radius of the cylinder is r, which I've drawn here, just going from this axis that goes through the middle of the cylinder. And then the line charge is denoted with lambda. So as we're given in the problem and shown in the example, the electric field is lambda over 2 pi epsilon naught r. Epsilon naught is our universal constant, 8.854 times 10 to the negative 12 coulomb squared per Newton times square meters. So I've just made a note of the constant. We're looking at the area of the cylinder, so that total area is 2 pi r times L for the total area. And then the angle for the electric field, so it's normal to the curved surface of the cylinder, and it has the same magnitude at all points along the surface. So phi is equal to 0 degrees as we're looking at the electric field just going through this curved surface and stemming out in all directions. So when we want to find the electric flux, that's our basic definition for electric flux. The electric field times the area times the cosine of the angle phi. But we already know the angle phi is 0. So we just plug in the pieces that we have for the electric field, the area, and the angle. So the electric field is lambda over 2 pi epsilon naught times r times the area, which is 2 pi r L, times the cosine of 0 degrees. Cosine of 0 degrees, though, is just 1, so that's an easy calculation to make. And then we have lambda over 2 pi epsilon naught times r times 2 pi r over L. Well, we see we have 2 pi in the denominator, in both the denominator and the numerator, so that term cancels out. So the 2 pi term cancels out. The term r cancels out as well because it's in the numerator and denominator. So that leaves us with the electric flux as just lambda times L over epsilon naught. So that's all we need to solve the problem. We just plug in the numbers. Well, in part A, we're given the radius is 0.250 meters and the length is 0.400 meters. So we just plug that in. We see the radius term disappears, so we don't even need to know what that numerical value is for the radius. All we need is our line charge lambda, and we were given that value as 3.00 microcoulombs per meter. I've already taken the liberty of writing this out instead of micro. That's just times 10 to the negative 6. So I've already plugged that in because we need everything in standard units. So that's just 3 times 10 to the negative 6 coulombs per meter. So we plug that in for lambda. Then we have L, 0.400 meters. So we plug that in for L. Plug our universal constant epsilon naught in and run that through a calculator. And we get the Electric flux is 1.36 times 10 to the 5 Newton times square meters per coulomb. In part B, we're asked, what is the flux of the cylinder if the radius is increased to 0.500 meters? So now we have a new radius, but our radius canceled out. So we have the exact same calculation as part A because the radius didn't even matter. So we have the exact same answer from part A. Again, 1.36 times 10 to the 5 Newton times meter squared per coulomb. And then part C asks us if the length is increased to 0.800 meters. That's just the exact same calculation again, exact same lambda, exact same universal constant. That hasn't changed. All that's changed is the length that we've plugged in. So plug in L equals 0.800 meters. And that gives us then a final answer of 2.71 times 10 to the 5 Newton meters squared per coulomb as the final answer for part C.